Hi, I'm Teresa, and I'm the instructor for Models in Science. Let me just give you a quick introduction of the course today, especially for people who are trying to decide whether or not it fits them. This might help you to decide, and also for people who are uh, confident on taking the class, this can give you kind of an overview of where we're headed. The course Models in Science is brought to you by the System Science program here at Portland State University. And so basically what we're going to be interested in is types of modeling that apply across a number of fields that are useful for researching, for studying a number of systems. And in that way, it's kind of great because people from all different fields taking the course can share something in common in interest in learning and can basically find value in the course. I think I've found a lot of people who've really enjoyed the course, so I hope you will as well. There's kind of three elements to the course. This is in the syllabus in a little more detail, but I can give you kind of the gist of it here. The first element in the course is going to be defining scientific modeling. What we mean by scientific modeling in this course is actually very specific. We mean models where you can do an experiment on them to learn more about a target system. So a lot of times we can't experiment on a target system directly. It's not feasible, it's not financially possible, it's not ethical. For a number of reasons, you might not be able to experiment on the real system, but you still want to learn more about it. So we'll create a model of the system and we'll do our experimentation with the model instead. That also helps to generate scientific knowledge and to contribute to what we can call basic scientific discourse. So not trying to apply what we've learned in science to improve things, but actually trying to learn more about how things work. So one element of this course is going to be just really fleshing out the definition of scientific modeling and sorting what things fit and don't fit within that definition. The second element of the course is going to be finding examples of scientific models that are used in research in the world and evaluating and critiquing them, describing how they were made, what they're made of, and what knowledge they've been able to contribute to science and in terms of learning about systems in the natural world. The reason that this evaluation and analysis is really important is because we have to always keep in mind that when you're not experimenting on the system directly, and instead you've made a model of the system, well, the model is always going to be different from the system. So when we try and gain new information about a system indirectly by studying a model of it, we have to always kind of take that with a grain of salt and keep in mind, in what ways is this model insufficient to be totally confident in the knowledge that we gain. So we can never be completely confident, but we can try and make a good case for being reasonably confident in the knowledge that we gain from experiments on scientific models. So there's going to be some critical thinking and some evaluation and analysis of scientific modeling that's important to kind of understand its merits and also its limitations in scientific research. The third aspect of this course is going to be kind of a synthesis where we're going to take what we know about the definition of scientific modeling, take what we know about different fields that it's been applied to, and what I want you to really do is evaluate kind of the merits of scientific modeling as a whole in a couple of fields that you choose. So you'll pick a field that's interesting to you, maybe some form of cancer in biology or something, and you can evaluate, you can summarize like how is modeling relevant in this field, what are we learning from it, and do you think it's useful, what are the strengths and limitations of modeling in a field that you like. So this is the part where you can take kind of what we share in the course, your understanding of the definition of scientific modeling and its strengths and weaknesses, and you can kind of relate that to a field that's interesting to you and share it with the rest of the people in the course, which makes for a pretty rich learning experience and a lot of really fun and interesting examples. So let me tell you a little bit about the rhythm of the course too. The course, each weekly each week we're going to have kind of a section of the course with a new topic each week, and there's going to be kind of three chunks in it. There's going to be a main session, which is like now you'll have some kind of video online that you'll watch, and there will be some questions that you'll need to answer for it. The assignments online on D2L are going to be, technically they're quizzes, but they aren't quizzes in a sense that you have to memorize and regurgitate information. You can keep the quiz open while you're watching the videos, and you can answer the questions as you go. Or also you could go look at the quiz ahead of time, see what the questions are, and then watch the video, kind of like knowing what things to pay extra close attention to. So I'm using a quiz format because it's easiest for submission and grading purposes, but it's not like, there won't be a weekly quiz in the sense of like drilling you for information. So, but there will be like a video each week that you'll watch. Pay special attention to a few key points that I'm going to draw out, and each week we'll focus on a slightly different topic. The first few weeks we're going to be working on the definition of scientific modeling, and then after that we'll go through a few different types of modeling. So we'll do like a week that's on animal models, a week that's on physical models, and there will be a couple of types of computer simulation and also mathematical models in there. So we'll have 5 different types that we'll explore, kind of one each week. In gearing up for a main session is going to be what I'm calling a pre-session activity. Basically, it's like trying to get trying to just kind of get your mind engaged for that topic. So on the weeks that we do a computer simulation, I'll have an online tutorial for you that you'll just go and like play with the software. There's free software you can download. You can kind of play with it. You don't have to make a model ever. You don't ever have to make a model. So if you're worried about that, don't be. But you do I do want you to play with the computers, with the ones that are computer simulations. I do want you to play with them because it's like a way to get a good feel for what that type of modeling is about. So so on those weeks you'll do kind of like an online tutorial with the software. Other weeks you might be reading an article and reflecting on that. There's some weeks where I have you watch videos. So you'll do some kind of activity, and then it'll be just same as the lectures. There will be an assignment connected with it where you'll just fill in some answers. You can look at them ahead of time to help you kind of prioritize your reading or whatever, but you should know that there will be always kind of like a pre-session activity, like a reading or video, and then answer some questions. Then the main session video where you'll answer some questions, really with my talking about like the core information on that topic. And then following up, there's going to be a post-session assignment, which is always in the form of online discussion. So if you're not familiar with D2L, there's online forums where you can basically post a chunk of content that you've written, and then you can also reply to 2 other people's content that they've posted. So each week you'll also have, following the video lecture, you'll also have something where you go online and you contribute 1 post and 2 replies to the other people. A lot of times these posts are going to be in the form of, go find an article that features a scientific model and, critique it. Describe how they made it, describe what they learned from it, that kind of thing. So it might get a little repetitive in terms of, like, each week we do a kind of modeling and each week you'll look for an article. But it does make it kind of transparent, predictable, and, it just kind of follows a rhythm. So in that sense, it's, I think, very organized. I might be a little bit too organized, but I hope it's helpful in the course. Okay, so here's an overview of what the grading looks like in the course. The pre-sessions are each worth 3 points, and there's 10 of them. There's not one this week, but there will be one every week hereafter, and they're always due Mondays. So you'll have a pre-session due this upcoming Monday, where you read an article and answer some questions. Then the main sessions are always due on Wednesdays. There's going to be 9 of them, 9 times where you're going to watch a video and answer a few questions. Each of those are worth 1 point. And then there's going to be post-session homeworks where you go, so after, the online discussions, there's 11 weeks in the term, and there's 1 each week where you'll go and write something in an online post and reply to 2 people. Those are worth 3 points each week, and there's 11 of them. There's also 2 quizzes. So the quizzes, there's a midterm quiz and a final quiz. The midterm quiz is basically about what is scientific modeling. So basically, before we explore a bunch of types of it, it's really important that I make sure everyone's on the same page of what fits in our course definition and what does not. So that happens after week 4, the midterm quiz, and all the questions are like, I'll give you a little research vignette. You know, researchers Bob and Joanne are doing XYZ research, and then you have to pick at the bottom, is this scientific modeling or not? Like, it's like a true or false, you know, you just pick if it fits or doesn't. There's 11 of those, I think. That's the essence of the midterm. And then the final exam is a little more nuanced than that, because I'll be telling you things like, here's a research question that they want to ask, which type of modeling would be most appropriate. So you might pick, oh, that's good for animal modeling, or that's good for simulation, or, you know, you can pick. At that point, I want you to be able to pair certain types of research questions with certain types of modeling that would be a good fit. And I want you to be able to talk about evaluating how do we know whether a model is credible. You know, can we really trust the information that's coming out of that model or not? So that one will be like a little deeper than just the definition by the time we get to the final. But it's also going to be multiple choice format exam. I think there's maybe 13 or 14 questions in the final. There's also 2 applications where I'm wanting you to take what we learn in the class and apply it to a field of your interest. So basically what I'm going to be doing is, what I'm going to ask you to be doing is to pick a field where you're seeing like at least 2 types of modeling used. So like maybe you're interested in a certain type of cancer, and you might say, oh, they've done computer simulations to learn about that, and they've also done animal modeling to learn about that. So let me, you know, so then you can summarize like how modeling is useful for that field. So there's going to be 2 times where one of the online discussions is going to require you to do like a little deeper than find an article and critique it, but a little more like look at least a couple examples of modeling in a field and summarize how modeling is useful in that field. You know, kind of apply kind of more of an application spin than a summarize and critique spin. So that's all of the pieces that there are in the course. Let me give you a couple of examples. Oh, sorry. First, let me tell you some important things. First important thing I should tell you is what people really like about the class, and the second important thing I should tell you is what people maybe don't like so much about the class, just to give you fair warning in the kinds of things that you might encounter that you might not like. So the thing that people tend to really like about the class, and I'm not counting D2L. So some people love that it's online and asynchronous, but then other people just really hate dealing with D2L. So independent of that, there's also this aspect of people enjoying in the class that we kind of share some common curriculum of what is a scientific model and what's the essence of scientific modeling. So that's something that we're all chewing on together and have kind of as common ground. There's a nice balance between the common ground and also being able to go find examples in a field that you care about. So there's some shared material, and then there's some material that you're bringing from a field that you're interested in. I think people really like having that balance of stuff in common with their classmates, but then stuff that's unique to their own areas of study. What's a little bit tricky about the course comes down to the definition of scientific modeling. So I'm aware that there are lots of kinds of models that are used in science, and they're very, very, very wonderful and useful. For the purposes of our course, in part just to make it a bite-sized chunk of material that can fit into one term, we're really focused only on models that are used to experiment on for the purpose of generating scientific knowledge about a target system that we didn't experiment on directly. So what people sometimes find throughout the term is once they kind of get their mind wrapped around the definition of a scientific model, they might have a realization that, most of my interests actually are more about design. Mostly I'm interested in optimizing things or making them as good as possible, and I'm realizing now that I don't have a lot of interest in like basic science of learning how something works. I don't necessarily want to learn how things work. I want to know like how to make them as good as possible. So if your interests, a lot of times people run into this with like engineering. If your interests are in making the thing as good as possible, then it might be kind of a poor fit for you in the sense that you'll be a little bored when you have to go look up like some biology article and critique an animal model when maybe that doesn't fit necessarily with what your natural interests are. You can definitely still find stuff and understand it. It's just, it might not be what you thought it would be when you sign up for a class called Models in Science. So the kinds of things that we'll exclude that people don't expect when they first start out are models for design purposes. This could be engineering, but it could also be clinical trials, like with drugs. Say drug testing with animals. That's a great example of something that we can't count in our class if all you're doing is giving, say you have say there's two versions of a drug and you're wondering which one works better. So some of the mice you give drug A, some of the mice you give drug B, and you watch and see which group does better. That's beautifully important to do in the world. But if you're not also paying attention to why, you have to pay attention to why did the medical problem happen? Why is this drug working? Why is it more effective than the other one? If you don't care because you're just trying to make the best drug, so you're just going to pick whichever one has the best outcome and sell it, in that sense, I'm calling that a design orientation. You're not trying to learn more. You're not trying to generate scientific knowledge. You're trying to make the best ever drug. It's the same as making the best ever widget. It's the same as designing the best ever policy. In that sense, you're just trying to do more of an applied science, like use what we know to make the best possible decisions. And that is hugely important, but of a decidedly different flavor than what we're calling scientific modeling. Here we're interested in just learning more about the target system. Not improving it, but just learning how does it work, what are the active ingredients, what makes it tick. So we don't consider design. Another thing that we don't consider is statistical analysis, and a bunch of related approaches where you're summarizing data you've collected on the real thing. So statistics will a lot of times talk about models, but the way that they make those models is by measuring all these things in the real system, and then a statistical model, in effect, is just summarizing what measurements you've seen. So you might give a lot of surveys, you might take a lot of measurements and take a lot of records from things, and then you can analyze them statistically and test them statistically, and what you'll come up with is a model that summarizes what you observed in the real system, maybe gives you some kind of confidence intervals or a statistical test of how confident you can be, of how likely the outcome would be of what you saw. That all has to do with measuring the real system, and that's also qualitatively different than creating a model separate from the system and tinkering with the model. So here we're only interested in models that you experiment on the model instead of the real thing. We're going to be experimenting on a model and making synthetic data in a sense. So that's decidedly different from all these efforts like data mining, machine learning. All these things are ways to analyze real data from the real world rather than to conduct an experiment on a fake version of the system that you care about. And I don't know if I mentioned this, but I should definitely emphasize that at no point do you have to make your own model, not even the computer simulations. Like I want you to play with them. I want you to play with a couple models that have already been built, and I want you to read about them, and I want you to think critically about what we learned from those models and how well we can trust it. But you never yourself have to make a model. So I hope no one ever gets that false impression. So forecasting is similar to statistics in that it's taking data. Forecasting is like prediction. So it almost sounds similar to say, like, I want to learn what's going to happen in the future, but prediction and forecasting are also of a really different flavor than the kind of statistical modeling that we're interested in. A lot of times things that are very good predictors of what will happen in the future are actually really lousy at teaching us why something works the way it does. So you might have a model that takes all historical data of weather and is an awesome predictor of whether it's going to rain tomorrow. That kind of model is not really helping you learn what causes rain, why rain happens, that kind of thing. It's just it's a different purpose for the model. So when we define scientific modeling, it's going to be part how you make it, but a big part of it is going to be your purpose for using it. That you're trying to use it to experiment on the model instead of the real thing to learn more about the real thing. And that's a definition that some people, once they chew on it a little bit, they kind of come to terms with, maybe my interests are actually not going to fit quite within that boundary, and in that sense the course is slightly less interesting to me. So bear that in mind, maybe treat that as a disclaimer, or consider this the disclaimer or the fair warning that we will have a pretty narrow definition of scientific modeling, and we'll find tons of examples, but it's not quite as wide open as you might think from a title like Models in Science. So bear that in mind. So let me give you a couple of examples of scientific models that I think are interesting and pretty accessible. The first one is using animals as models of addiction in humans. Historically, there have been a lot of experiments where we give narcotic substances to, say, rats and follow the patterns of addiction in rats to try and learn more about how addiction occurs in humans. And some of the kind of foundational experiments done in the early 20th century would have a rat in a cage with basically 2 bottles of water. One of them's got just plain pure water, and the other one's got water with morphine in it, or something like that. And predictably, the rats would favor the water with morphine over the regular water. They would get very addicted, and at some point they would stop even eating or doing basic functions and would die pretty soon. That has really flavored our mentality about what causes addiction as being the substances themselves. That the substances kind of hijack your brain, and they get these kind of chemical hooks into you and control your behavior and change kind of your ability to carry out your life. So that's really influenced the war on drugs and a lot of policies revolving around addiction by flavoring the way we understand addiction to occur. So in the 1970s, a man named Bruce Alexander, he kind of questioned this philosophy about the causes of addiction, and so he built what he referred to as Rat Park. So he built basically, instead of a small cage with 2 bottles of water, he built like a huge space, plenty of room, lots of other rats to interact with and mate with, lots of toys to play with, lots of good food, and basically just a fabulous place to be for a rat. His cage also included the 2 bottles of water. One's just pure water, and one is the water with morphine in it. And what he found is that rats in this situation did not become hopelessly addicted to the tainted water, and actually they preferred the plain water. And he did several variations on this experiment where he would even take rats from the old style of experiment who had been basically forced, put in a situation where they became very addicted to the morphine. Once they were placed in the Rat Park instead, they went back to preferring the plain water, basically because they had a really fun life to live in the bigger cage that he had built for them. So what knowledge was generated with this Rat Park model was more of a questioning of the way that we have viewed the causes of addiction in the past. So the way that people have interpreted this research is to rethink what does addiction mean, what causes addiction, and is part of the development of an addiction based on the circumstances that people live in and the alternatives to basically drug-based coping that they have for engaging in life, engaging in social interactions, and kind of bonding with other important facets of their life. So it brings into question the way that we've understood addiction in the past, and it suggests maybe different ways that we could consider dealing with addiction in the future. A lot of this research was summarized by a man named Johann Hari, and he's actually got a TED Talk that's really interesting. I'll post a link to it if you want to learn more about that. But basically, this is a really good example of animal modeling because one, it's doing experimentation with animals to learn more about humans via research with the animals, and two, it's not just doing it with it has the purpose of generating new scientific insight. It doesn't only have a purpose of figuring out which is the best detox drug and has the least overdoses or something like that. Instead, it's really helping us to learn, like, what are the underpinnings of addiction? What is the inner workings of it? Why does it happen? So that would definitely be an example of scientific modeling that would fit squarely in our course definition. The second example I'll share with you is a system dynamics model of health policy. System dynamics is a type of computer simulation that has its foundation in sets of ordinary differential equations. We'll talk about this in one of the weeks. I think it's week 9. We'll talk about system dynamics, numerical models where you have a bunch of equations interacting as the foundation of a model. We won't go very deep into the math, so don't be alarmed by that. But you can know at the top level that these models are made of equations that you solve repeatedly and show patterns over time. So in this example, a system dynamics model was made with equations to represent the U.S. healthcare system. And basically, they tried to capture all the essential elements that they saw operating in the U.S. healthcare system with an eye toward learning why policies have the impact that they do on basically 4 outcomes of interest. They're interested in health equity, which means, like, what's the gap between the very healthy and the not healthy, and access, how easily can people acquire health care, what's the quality of health care that people are able to access, and also the cost of health care is a big concern when we're thinking about health policies for the future. So what these guys did is they represented the healthcare system of the United States, and they basically interacted with it to see if they could learn why health policies affect these 4 outcomes in the ways that they do. So they tried a bunch of different healthcare policies, and they've mapped out kind of like what the impacts were. What I should clarify here is that if the researchers had simply tried out a bunch of policies and then just reported back, say, to Congress which one was most effective and tried to just push that one through, like maybe they would just look at which one's the cheapest, or maybe which one has the lowest rates of death or something. If they had no attention toward learning why that one would work better than the other, or how does the system work, then we would consider this more of like a design orientation. But they were also very interested in how the system works, how the health system works in the United States, and why policies sometimes have counterintuitive outcomes. So one counterintuitive outcome that they found in playing with this model that they built, was when they tried an intervention that simply expanded health coverage to be universal and demanded a high level of quality of care, the counterintuitive outcome to doing simply those 2 things was they saw in the model that there was an increase in the amount of inequity in health. So that means that the gap between the people who are very healthy and the people who are not very healthy increased. Now, this is a counterintuitive finding. You would think that if you just demand high quality care and expand care to everyone, you wouldn't think that there would be an even bigger gap between the really healthy people and the health of the unhealthy people. Well, the reason when they kind of explored into the model and what's causing this, what they learned is that especially in areas where there's not a lot of coverage, if you suddenly expand coverage, there will suddenly be a huge demand on the healthcare infrastructure there. So there will be a huge demand on clinics and hospitals to provide care to all of a sudden a much larger population of people. And so what they found was if you do that, you need to also pair it with efforts to expand the capacity of the healthcare system, like get a lot more doctors and nurses in the game. And they also found that if you can orient people toward a lot more of the preventative care, then that was the way that they were able um, to that was the strategy that they came up with that was like most effective. And the reason why that they posited was because if you'd simply expand coverage and demand the same high quality care that you would want, then you'll have areas of the country that will be overwhelmed with a suddenly huge need for healthcare, and the care there will be much less than you would expect. They won't be able to absorb the volume. So, so this is an example of a computer simulation where they're doing experiments on a computer simulation instead of actually trying out a bunch of healthcare policies and observing what happens in the real world. This kind of model looks like it's doing some kind of prediction, which is something that I said that we were going to exclude in this class. Because if you can look out, it's kind of saying, you know, where the trend would go in the future. Well, I would argue that this type of model is going to actually be a really poor predictor of, say, the exact cost of the healthcare policy in 2020. What they have kind of an eye for like general trends in the future, but they're not trying to precisely predict like how many people will be sick, how many people will die. Their main emphasis here is not really on prediction, but it's really on understanding how the system works. So in that sense, we are including it in our course definition. It's a little bit different of a spirit, although you might try and use this for a general prediction in the future. The spirit in which they're using it is more with an eye toward understanding how the system works. And in general, usually when you use a model to understand how a system works, it's usually a weaker predictor, it's usually less accurate of a predictor of the future. You do a better job predicting the future with other methods that are different from the kinds of modeling that we'll use in this class. The types of modeling that we'll cover in this class are usually pretty lousy at accurate prediction in the future. So that's an important distinction to keep in mind. These two examples of models together are something that you might do in one of the application assignments. So the application assignments, I told you, you're going to pick a field that you're interested in and find a couple of types of modeling that are used to learn in that field. So if I were doing that assignment, I might say, hey, I'm interested in healthcare, and so let's see, I can find one example of animal modeling that's used to inform the way we deliver healthcare to people to help them with a problem, and then in this case of addiction, and then I'm also interested in this computer simulation of numerical modeling and how that is used to help us learn about healthcare in the United States. This would be the kind of thing that you could summarize. Here's the ways I think that this is useful. Here are the things that we need to bear in mind when drawing information from here. So, so that's a little bit of an overview of the course. What I want you to do next, if you're still interested, is look at our course space on D2L. Check out the syllabus and the other things. I think I've covered all the major points in the syllabus, but it's good to glance through just to kind of know where the information is. Look at the format. Make sure you understand the format for kind of what's coming up next. I'm going to have things posted in the calendar, so it should alert you when there's a deadline coming up. But you'll need to be able to navigate D2L since it's a fully online course. So if you have any bugs in that, it's a really good time to email me now so we can make sure you're squared away. The next things coming up are going to be the post session after this lecture, which is going to basically be introduce yourself. So you'll write a post, introduce yourself, and reply to 2 people. So do the post session for this week, introduce yourself, and then there will be 2 things for next week. The pre-session for next week is going to be due Monday. You'll read an article and answer some questions, and then the main session is going to be due Wednesday. That'll be another video from me where you'll watch the video and answer some questions online. So email me if you have any questions, and I hope you're excited for the course. I am.